With the simple model of the Earth's greenhouse effect under our belts, let's now look at the average annual radiation budget of the actual planet. This diagram shows elements of the annual radiation budget of planet Earth. This is taken from the fourth assessment report of the IPCC and is based upon measurements from satellites and also at the surface. Let's begin by recognizing that on average 342 watts per meter squared of radiation is incident at the top of the atmosphere. This is the total flux of radiation at the radius of the Earth's orbit divided by the surface area of the planet. Of these 342 watts per meter squared, 77 are reflected by clouds and aerosols in the atmosphere and also backscattered by the atmosphere itself. And another 30 watts per meter squared is reflected from the surface, giving a total of 107 watts per meter squared of reflected solar radiation. 67 watts per meter squared of the incoming solar radiation is absorbed directly in the atmosphere by clouds and by certain gases, leaving only 168 watts per meter squared to be absorbed by the surface. This is less than half of the incident solar radiation. Now, in equilibrium, the amount of energy absorbed by the surface has to be balanced by the amount of energy emitted by the surface. So let's look at the emission budget. To begin with, the surface of the Earth emits about 390 watts per meter squared of radiation upward, of which 40 watts per meter squared essentially goes directly to space. The rest of it is absorbed by greenhouse gases and by clouds in the atmosphere, and there is a back radiation of 324 watts per meter squared. This is rather astounding because it's almost twice as much radiation as received directly by the surface from the sun. That is, the Earth's greenhouse effect is so powerful that on average the surface of the Earth gets nearly twice as much radiation from the atmosphere as it does directly from the sun. So in the end, there is only a net emission from the surface by radiation of somewhat less than 70 watts per meter squared. But radiation is not the only way that the surface can emit energy. The other way is by direct conduction of heat to the atmosphere, which accounts for about 24 watts per meter squared, and by evaporation of water from the ocean and from wet land surfaces, leaves of plants and so forth. That amounts to somewhat more, 78 watts per meter squared. It turns out that evaporative cooling of the surface is the major means by which the surface of the Earth cools, particularly so in the tropics. So at the end of the day, about 235 watts per meter squared leaves the atmosphere, which balances the next incoming sunlight once you've subtracted off the amount that's reflected to space. So we see that the real radiation budget of the planet, as measured by radiometers on satellites and by measuring processes going on at the surface of the Earth, shows this powerful greenhouse effect, whereby almost twice as much radiation is received at the surface of the Earth from the atmosphere as directly from the sun.
Let's talk about some of the more detailed aspects of the Earth's radiation budget. Let's begin with this map created by NASA from satellite measurements, showing the annual mean clear sky albedo, which is principally the reflectivity of the surface. These are made by making measurements at places and times where there happen not to be clouds, and then assembling those measurements over the globe. Let's first look at the albedo of the ocean. Notice that this is principally a function of latitude, with quite low albedos, less than 0.1 at very low latitudes, increasing to higher albedos toward the pole. Why should the reflectivity of ocean water be a function of the latitude? Well, this is simply because the fraction of solar radiation incident on water that's reflected depends upon the angle at which the sunlight hits the water, and that angle is in general shallower at higher latitudes. The really interesting variations of albedo occur over land. So let's have a look at these. Notice that there's fairly high albedo over the Sahara Desert in Saudi Arabia. This high albedo results from the fairly bright surfaces of sand and other things that make up the desert. We see high albedos for similar reasons in the interior of Australia. We also see relatively high albedos over Tibet, and in Central Asia. This is principally owing to snowfall in the wintertime. that persists into the spring. And as we go to even higher latitudes, we see regions like Greenland of extremely high albedo reflecting almost permanent ice cover. This is one aspect of the reflectivity of our planet, but only one aspect. A great deal of the net albedo of our planet results from clouds that are not shown in this particular diagram.
Let's look at some other detailed elements of the radiation budget as measured by satellites. These are very effective in measuring the radiation budget at the top of the atmosphere because they're relatively unbiased measurements. We have good instruments. The orbits of these instruments are such that each part of the planet is sampled roughly equally. This shows the calculation of the mean absorbed solar radiation. So to make this calculation, we measure how much sunlight is coming in from the sun and subtract off the part that's reflected locally by the planet, that is by the surface and by clouds in the atmosphere. And that difference has to be the mean absorbed solar radiation. So what one sees on this map is that anywhere up to about 340 watts per meter squared is absorbed in certain regions of the tropics. These tend to be regions which are relatively free of clouds, so there's not much sunlight reflected. That total absorbed solar radiation drops off with latitude, and it goes down as low as 60 or so watts per meter squared near the pole. So there's a strong latitudinal gradient in the absorbed solar radiation. Much of that is explained by the different incident angles of sunlight as one moves from the equator toward the poles. The chart over here on the right-hand side of this diagram shows the longitudinal mean or zonal mean of net absorption of solar radiation. This next map is the same thing but looking at the long wave or terrestrial end of the spectrum. This is the mean outgoing long wave radiation, once again measured by measuring the upwelling long wave radiation from the planet. This also shows a strong latitudinal gradient in emissions, with the strongest emissions actually occurring not right at the equator, surprisingly, but in the subtropics regions here. Now this turns out to be regions which are relatively free of clouds. Clouds absorb a great deal of outgoing long-wave radiation. In cloud-free regions, especially regions which are dry and also have not much water vapor absorbing this outgoing long-wave radiation, photons can get from very low in the atmosphere directly to space. And it's these dry, fairly cloud-free subtropical regions which are responsible for much of the emission going on from the planet. These areas, these dry, somewhat cloud-free areas of the subtropics are sometimes referred to as the planet's radiator fins. It's where the radiation is going out. Relatively small amounts of radiation leave the planet at the poles simply because the temperatures there are quite low. The Stefan Boltzmann law tells us that we should have relatively low emissions for that reason alone. Once again, the chart over here on the right shows the zonal or longitudinal average emission of long-wave radiation by the planet, showing this double peak. These two peaks correspond to the Earth's subtropics, which are relatively dry and relatively free of clouds, and where radiation can escape relatively easily to space. There's a local minimum near the equator where there tend to be more clouds and water vapor. This chart shows essentially the difference between the previous two charts, giving the annual mean net absorbed radiation. So we see most of the radiation is absorbed again in the tropics. The zero line is in the high subtropics or mid-latitudes here, and poleward of that line we have a net emission of radiation to space. So there's generally speaking, a north-south gradient in the net absorption of radiation. Once again, over here on the right, we have a chart that shows the longitudinal average of this quantity, showing that in the tropics we have a net absorption of radiation, and at high latitudes we have net emission of radiation. Now, for the planet to be in balance in the whole, averaged over the entire surface area of the planet, this ought to be zero. It isn't quite, and that's because the planet right at the moment is not in equilibrium. It's warming up. There's about a 1 watt per meter squared excess absorption going on. Looking at this spatial pattern, we see that for each part of the atmosphere to be in equilibrium locally, there has to be something to compensate for the fact that there's a net absorption in the tropics and a net emission in the poles. For everything to work out in equilibrium, there has to be some way of getting energy from the tropics to the poles. That is, we need to get energy from the regions where it's absorbed to the regions it's emitted. If we just look at how much transport we need, that's given by the black line on this chart. So this shows the inferred net transport by the Earth's system, and that turns out to be mostly, almost entirely, the ocean and the atmospheres, as a function of latitude from the South Pole over here on the left to the North Pole over here on the right. So as we go northward from the South Pole, we see that we have a negative transport. That means southward transport of heat by the atmospheres and oceans, reaching about zero at the equator, and then north of the equator we have a net northward transport. So in both hemispheres, the oceans and the atmosphere transport heat from the regions where it's absorbed, the tropics, to the regions where it's emitted, the higher latitudes. This chart also shows a decomposition of this transport between the oceans, given by this dashed line, and the atmosphere, given by this dashed dot line. Now, these are estimates that are based upon direct measurements of transport processes in both fluids, and there are fairly large error bars on them. We will come back to talk about the mechanism by which the oceans and atmosphere transport heat later in the course. In the next video, we'll talk about how the Earth's radiation budget varies with seasons and otherwise.